Okay, so let's continue with the parameters for your gold dissolution. The effect of oxygen pressure on cyanidation. So at low cyanide concentrations, um, oxygen pressure actually has no effect on the rate of gold dissolution. However, it begins to be very important at high cyanide concentration. Um, the reaction rate begins to be dependent on oxygen pressure. Okay, so we are saying here when your cyanide concentration is very low, then the oxygen, the pressure, the partial pressure of the oxygen here has very little effect on the whole process. However, when it is now quite high, this oxygen pressure now begins to play a um, a very important part in the dissolution of gold, and the the concentration of actually of this cyanide is actually independent and will not affect. Maybe it will be very constant at a certain point in time, but when you now begin to increase your partial pressure, it means that your rate of dissolution will actually go very high. Okay, so this is again another experiment that has been done to show your concentration here of your cyanide, and here I've got your rate of dissolution here, and then we are comparing 3.5 atmospheres and 7.48 atmospheres. Okay, so we can see here that at at low concentrations here. This is a low concentration here. At low concentration of your low concentration of your lixiviant here, you can actually see that even at a high pressure of 7, the rate of dissolution is actually much lower than at 3.4 atmosphere. So you can see that 3.4 atmosphere, when concentration is low, produces a higher rate of dissolution. However, when your concentration of lixiviant begin to increase here, maybe after zero point 0.1 here, you can see that now the 7.48 begins to have a higher rate of dissolution. So here, um, what is more at play now is your 7 point your atmosphere in high concentration. It means that your in high concentration, they do not they play a lesser role in dissolution of gold. What plays a critical role now is the change in your partial pressure, or the pressure of the dissolved oxygen. Okay, right. So oxygen mass transfer um, decreases with increasing slurry pulp and density, and also decreasing particle size. Okay, so what are we saying here? The major influence on oxygen mass transfer rate to the solution has been found to be the superficial air velocity, which is defined as the airflow rate per unit cross-section area of the leach tank. Okay, so that's the superficial air velocity, which is the major influence on your oxygen mass transfer. Okay, and we say your oxygen mass transfer therefore is affected by slurry or your pulp density, and also your particle size. Some time ago, a tech mine process used to use pure oxygen. I'm not sure about now if they're still continuing to use pure oxygen for their leaching process. Okay, then we also have what is pressure cyanidation. When you use now, when you use this is high pressure, temperature, and concentration of cyanide, right? So here you can have your recovery, and here you can have your temperature, pressure, and your cyanide. Okay. Now we're simply saying that when you use a combination of this high temperature, pressure, you also see that your rate of recovery is seen to go up when you increase your temperature, pressure, and the concentration of your cyanide. Now, this process is actually for treatment of maybe refractory ores that are stubborn to the conventional leaching methods. So this is when you use this combination not only of your pressure, but of your also temperature and also of your cyanide. Okay. Now let's look at the effect of pH on cyanidation. Right, a pH is usually a measure of alkalinity or acidity in a solution, and it is actually calculated in terms of the concentration of your proton. Okay, so in gold leaching, pH modification is done usually by adding lime, at times caustic, but if you are doing it prior to milling, you'll be adding usually lime, which makes the slurry alkaline, and also why at the milling stage you can actually condition your ore before it actually reaches the leaching stage. Okay, so lime is added to the slurry to keep the pH in alkaline conditions. Now it has got the following effects. Now, why do we add lime? Because we said we want to keep our conditions in alkaline pH. So when we keep our conditions in alkaline, when you keep our conditions in alkaline state, what actually are we doing? We are actually preventing cyanide loss first of all by hydrolysis. Okay, what's that? We'll look at that in the next slide. We are also preventing cyanide loss by the action of carbon dioxide in the air. How is that? Okay, we'll look it in again in the next slide. Then we also helps to decompose your bicarbonates in the mill process water prior to using it in your cyanidation. You don't want your carbonates to be present in the cyanidation process. Okay, then you're also neutralizing acidic compounds such as salts, your ferric salts, and other sulfates in the meal before adding it to the cyanide circuit. Okay, so these are acidic compounds. So before you actually add cyanide, you want these acidic conditions to be removed, and we said we want some alkaline conditions. Okay, then we neutralize acidic constituents such as your pyrite that is in the ore. So these are the effects or the benefits actually of keeping your conditions in alkaline state when you're doing leaching. There are a lot of things that you are preventing, and of course you are optimizing your process and giving conditions for your leaching process to be in the best state. However, there are also other parameters and other reaction side reactions that you also don't want when this system goes in the acidic region. So that is what you want. Okay, so we say the hydrolysis of your cyanide ion. This is the reaction for your hydrolysis of your cyanide ion. Okay, so your cyanide is forming your HCN here, your HCN gas. Then there's also decomposition by atmospheric carbonates. So your CN here is actually decomposed and also forms hydrogen cyanide gas by atmospheric pressure, and you also don't want that. Okay, why don't we want hydrogen cyanide? Hydrogen cyanide forms an insoluble AuCN, which is liberated in all these cases, and we actually do not want that. And also, hydrogen gas is actually very poisonous, and you do not want to produce this gas, and it has to be prevented at all costs. Okay. Then you also do not want also to have your pH to be too high, maybe around 15 or so, for 14, 14, 15, 14, maybe around 14, maybe operationally wise. It also tends to affect the rate of dissolution of gold. Of course, you understand maybe some high pHs, maybe 12. You want to take care of maybe your copper, etc. It can be done, but at the same time, um, too high a pH can also have adverse effects on your dissolution. So you need to carefully optimize your gold dissolution pH. And as a rule of thumb, generally, most mines operate between a pH 10.5 to 12. That's the general pH that most mines operated. Maybe you can go maybe slightly higher or something like that, depending on the nature of the ore. Okay, now residence time, that's quite simple. Residence time in the leach is the time taken for the slurry to flow through the tanks. Okay, and when we're talking of residence time, the longer the residence time, the you're seeing simply mean that the longer the gold particles are in contact with the cyanide, therefore, more gold will actually be reached. So your residence time is actually determined by the volume of the tanks, your flow rate, and your slurry density. Okay, so your residence time is actually very important. It increases your time, your recovery. Now, when you increase your residence time, you find that your recovery also increases. So you have to optimize this residence time. Um, you have to optimize this residence time depending on the volume, slurry flow rate, and slurry density. Now you find that there are other ores that are slow leaching, okay, slow leaching, and there are other ores that are fast leaching, okay. So for your slow leaching, we are saying they've got a very for slow leaching, we are saying that they've got a very slow leaching profile. They might start out at the time very slow and then it increases. This is a slow leaching profile and then it increases at the end. Then there are also other that are quick leaching ores. So here automatically your rate goes up quickly. So depending on these characteristics of this ore, you can now then determine the flow rate, your slurry density, in order to optimize the parameters for your leaching. Okay, if you're fast leaching ores, then you need to know that your flow rate is might be also on the high side. If here your ore is slow leaching, then it might mean that your flow rate is a little bit on the lower side, so that you take as much gold as possible and you increase your residence time so that you take as much gold as possible. Okay. Now, what's the effect of agitation on cyanidation? Okay. Um, when you do agitation, you want to uh, mix efficiently your solids and your and your lixiviant. Okay, so agitation ensures that your gold complex ions um, forming on the surface of the gold particle are actually removed into the solution to allow access on the fresh gold particle surfaces for more unreacted cyanides to reach this gold particle. So agitation simply means that in our first lecture, we talked about the steps or the stages that are actually involved in the leaching process. And we say that we are moving from your bulk solution, then you go to the intersurface of your particle, and then there is a reaction, and when there is a reaction, the products begin to move into solution. Now this agitation allows, now as soon as this product is leached, it actually leaves this nucleus of the particle and allows more fresh surface to be in contact with the bulk solution, which is your cyanide. So in practice, this increases the rate of your cyanidation. Okay, so generally in practice, cyanide mixing can be done in what are called pachuca tanks. Okay, this allows the cyanide to dissolve completely and leads to more efficient mixing throughout the pulp. So here you can do what is your cyanide mixing first, and then you add your ore, and then you have got efficient mixing throughout the pulp. So again, here we've got your experiment here on your right, got your agitation rate and then your solution rate here. You can see automatically this this is your 4.1 milligrams per liter, and this is your 32 milligrams per liter. So we can see that with increase in agitation rate here, okay, your solution rate also increases. Okay, right. Then we've got the effect of temperature. Right. Generally, higher temperatures can lead to an increase in the rate of dissolution of gold. However, generally, it is not economical to heat slurry. So, generally, we in the conventional cyanidation methods, there is no need for us to use any heat. You can simply use atmospheric temperature and pressure to do economic leaching. However, for your refractory ores, of course, this might be very, very difficult. Okay. So the other disadvantage of heating is that when you heat, you reduce the capacity of your carbon to absorb the gold. Okay. First of all, you actually even lower the solubility of oxygen in the slurry. So it means that you reduce the rate, you reduce the concentration of your dissolved oxygen that is in the slurry. And we all know from the Elsner's equation that oxygen is important for cyanidation. So if you increase the temperature, you lower the solubility of oxygen, and it reduces in the slurry, and then you're also reducing the capacity of carbon to absorb the gold. So um, generally, gold dissolution is actually done at ambient temperatures, and there's no need for high temperatures for the conventional. Okay, now let's look at the effect of foreign ions on cyanidation. Now, we say we have what is an ore, okay, at the beginning. Now, an ore contains different minerals, an ore contains different elements, and some of them are unwanted, some of them are unwanted. Okay, so some of them are harmful to the process, some of them not harmful to the cyanidation process. Okay, now we have got some um, some some materials such as your pyrrhotite here, such as your pyrite, copper, zinc. Okay, and other base metals here. You also got your arsenic and the antimony, which are the most problematic, actually, uh, one of the most problematic materials to deal with in the gold cyanidation process. Why? Because these consume cyanide. Okay, you want your cyanide to react with gold, but because of the presence of these minerals, they also compete for cyanide together with the gold. Okay, so these base metals, they also form a stable complexes with the cyanide. Okay, therefore reducing its activity and retarding this process that we want, which is the gold cyanidation process. So it is retarded. Why? Because there is competition for the cyanide, as with the base metals, as they also form stable complexes with the cyanide. So because of the competition, it reduces the activity of the cyanide and retards the process that we want, which is the gold cyanidation process. Okay, so here are some of the stable complexes that copper form when they complex together with the cyanide in solution. So instead of this being gold here, it is now Cu. It's now Cu. Why? Because they form also a very stable complex together with the cyanide. Okay. However, for your copper, the rate of may not be the rate of your gold may not be affected when you keep significant excess of cyanide in the solution. If there is a significant excess of cyanide in the solution, then it might not affect the dissolution of gold. Okay. So as a rule of thumb, usually plants, they keep the total cyanide in solution over the total copper in solution at a ratio which is greater than 4. So you can see here that though more cyanide might be necessary, but it will lead to more gold actually being dissolved because there is excess amount of cyanide, and it keeps your copper cyanide ions in check. Okay. Now, the other problem that was copper, you can treat copper. Now we have got your sulfide minerals. Sulfide minerals are they are very problematic in the case that they react both with your cyanide and with your oxygen to form thiocyanate ions. So this is the problem of the sulfide minerals here. So here they are reacting first with your cyanide, and then they are also taking also the oxygen. So instead of competing with your cyanide only, they are now also competing with the oxygen. This significantly reduces the the rate of dissolution of your gold. So you find that pyrite is the most stable form of the iron sulfide. So though it might have some problems, but because it is very stable, you might get away with it. However, you have your pyrrhotite now. It is actually a serious cyanide. The pyrrhotite, its rate of decomposition it's much fast, um, and therefore it takes your cyanide and takes also your oxygen, which is very detrimental to the cyanidation process. So here we say your pyrrhotite here is prone to oxidation and it forms ferrous and ferric sulfides. Hence, it is not only wasteful to the cyanide, but also a serious consumer of the dissolved oxygen in the solution. Okay. Then you also have your arsenic containing minerals, your arsenopyrite, your relga, and your opiment. They are also associated with gold ores. When you also mine, you also see these as coexisting minerals, and they can also react the same by consuming oxygen and also by consuming your cyanide. Okay, so they are both cyanicides and they are also oxygen consumers. Okay, um, then you realize that stibnite is actually even worse than your arsenal pyrite in all these respects. Why it increases the rate of oxygen is actually rate of oxygen consumption is actually very high um, during the decomposition of stibnite. It generates thioantimonides and sulfides, and these may actually even be absorbed on the gold surface and further hinder the reaction with the cyanide. So in the case of stibnite, you are now dealing with three problems. Your cyanide is being consumed, your oxygen is being consumed, and now you have got a passivating layer or a jacket um, which is now hinder a sulfide passivating layer, which now hinders the reaction with cyanide. So this is a very detrimental problem. You can see that plants such as your Kemen mortar have got very serious problems when dealing with these stibnite ores because you have to treat these three fronts, which is very costly. Okay. Right, so that's the end of our second lecture, and here is your assignment number two. Okay, this is your assignment number two, not a presentation, but an assignment. Please attempt questions one, two, and three. Okay, thank you very much.